So for this screencast, what I wanted to do, this is week 7 screencast, and what I'd like to do is talk about some of the issues I came up with for worksheet number 4 in unit 2. And the first one I was looking at, well, actually with the group breakout group that we had for last week at the end. We were working on worksheet 4. We came to number 2. And it was interesting how, we kind of worked through it, and I guess I was just listening more or less. And a couple other folks, they surmised that the voltage would stay at 6 volts here, and that was in the problem. But then also the electric field would decrease if these plates were pulled apart. And at the same time, when that happened, charge would actually flow from the plates back to the battery. And then one of the class members asked why that was the case. And we could not answer that question. And so that really spawned a lot of digging and researching in terms of why charge would flow back through the battery if the plates were pulled apart. And I guess one thing is, when the plates are pulled apart, if you look at the equation of electric field equals change in potential over displacement, since the displacement's bigger, which is the denominator, the electric field strength would become less. And so that would mean that electric field would get weaker. Now, I can't exactly figure out why that would cause charge to go back through the battery. I know that as these plates would separate, the electrical energy would increase because of, again, the equation electrical energy is equal to charge electrical energy. Let's see. Electrical energy would increase because the distance between the opposite charges increases. I guess I was looking at a couple of videos, Khan Academy video, for example, and that was describing capacitance as the charge divided by the voltage. And so plates that are close together have a high capacitance, and plates that are far have a low capacitance. And I guess my thinking is that when the plates are closer together, you have more attraction between the plates, which would cause the charges to stay on the plates. Whereas if you move the plates further apart, there's not as much attraction between the plates, therefore allowing the charges to more freely move back to the battery and through the battery. And I guess the effect of the negative charges being so close together would cause repulsion, which would overcome that attraction between the oppositely charged plates. I'm not sure if that mechanistic sort of understanding is correct, but it's very interesting to think about. And so anyway, that was one of the issues. Another was I was working with neon bulbs because I wasn't sure exactly how to get them to light. And I was wondering, how are they different from LEDs? Well, okay, I understand that neon bulbs are basically gas discharge tubes, which allow which work no matter which direction electrons flow through the circuit. Whereas the LEDs are diodes, which will only work when electricity flows in one direction. And so I guess what we figured out, a colleague and I at our school, was we had a Tesla coil. And this was basically, I don't know, something like 5,000 volts. And so we put it up near the neon bulb, and sure enough, it glowed. But yet when I tried to make the neon bulb glow through a low voltage source, it would not glow. So there's a lot of voltage that needs to occur. High voltage and fairly high resistance so that you have low current, because too high of current will obviously burn out the bulb. And so I made basically we got a kit and made a vertical axis wind turbine, and made the coils of wire and then the magnets, which were rotating on the spindle, which was connected to the blade. And so I spun that around with a hairdryer, and when I had connected the diode in one way, it didn't work. I turned it around, and it worked. But then when I tried that with a neon bulb, it didn't work. And so that, again, I guess suggests that, okay, if you don't have a high enough voltage source, you're not going to be able to get a neon bulb to light. And so I thought that was interesting, and I guess I'm kind of curious to work with the capacitors tonight to understand more about them. And I'm not sure if we'll be using the neon bulb with that exercise. And then I guess I had another question about the worksheet. Let's see if we move on to let's see, 7. Number 7 I was looking at. And 7A, one thing I was wondering is whether or not your answer would be negative or positive. Because I'm not sure if, I guess this is moving. Maybe it's assuming that the charge moves from infinity 2.4 meters away from the point charge. And so I guess I just am not sure if it's positive or negative, because the way I did it was I did the V equals negative Q or negative K Q over R. And with that, if I keep my displacement positive, then that would result in a negative voltage, which I'm not sure, I guess, what that reflects. It suggests that the potential at infinity is less than the potential when it's 0.4 meters away. But anyway, so I'm a little confused about the sign on that. Another comment I wanted to make is that for 7B, I did it a little differently than, I guess, well, I did it 2 ways. One way, you can use the change in electrical energy equals Q times delta V, and that will give you an answer of 3.96 times 10 to the minus 4th joules. But then you can also use the equation electrical energy equals K Q1 times Q2 divided by R, and that also gives you the same value. And so I guess I'm just trying to make sure that the change in electrical energy equal Q times voltage, that works for any situation, whether or not it is a uniform field or a non-uniform field. Because obviously when you have 2 charges, point charges basically, or plastic sphere and a point charge, that it's not a uniform field, but that equation will still work to provide the correct answer. It is interesting that in the teacher notes for Unit 2, that equation is listed and it's described as for uniform fields only, or for uniform fields, I guess. That equation is listed. And that's delta, or the change in electrical energy equals Q times electric field times displacement. But that is a little different because the equation I was using here in problem 7B was the change in electrical energy equals Q times voltage. And so that doesn't require electric field to be known per se, but I guess that might just be electric field at a point, which could be different for different locations, even if it's a non-uniform field. But anyway,